All right, let's dive in. We're about to explore some of biology's biggest puzzles. But we're not just going to look at the clues. We're going to see how a very special kind of detective, the mathematical model, is cracking cases that have stumped scientists for years. You know, in biology, we can collect mountains of data. It's like gathering a ton of evidence from a crime scene. We know what happened, but that's not the whole story, is it? To figure out why it happened, you need a detective who can see the pattern, connect the dots, and reveal the motive. And that's exactly what these models do. They take all those clues from experiments and weave them into a story that actually makes sense. So let's open our first case file. We're going to start small, inside a single bacterium. But don't let the size fool you. In this world, making the right call, reacting just enough but not too much, is literally a matter of life and death. Okay, so here's the puzzle. Bacteria have these systems that are designed to amplify signals, right? It lets them respond super fast and super strong. But what if the signal is just a bit of random noise, a chemical that just happens to drift by? If the cell launched a full-blown response every single time, it would be a colossal waste of energy. So how does it know the difference between a real alarm and a false one? Well, the model pointed to this beautifully simple idea called sequestration. Just imagine the actual signal is a messenger trying to run to headquarters to sound an alarm. But scattered along its path are these sponges, other molecules that can just grab the messenger and hold on tight, soaking it up before it can get to its final destination. And here's where it gets really cool, because this wasn't just a theory. They tested it, and the results? They were just striking. This chart shows how tightly things bind, and a lower bar means a stronger grip. Look at that. The sponge molecule, NAR, grabs onto the signal messenger over 5 times more tightly than the intended target, mTRA. It's basically a molecular magnet, just pulling that signal right off course. So you see the principle here? It's genius. A weak, random signal sends out maybe 1 or 2 messengers. They get instantly soaked up by the sponges and nothing happens. But a strong, persistent signal, it sends out a whole flood of messengers. They completely overwhelm the sponges, and the overflow can finally race to the target and trigger the real response. It's an elegant, built-in filter for all the noise. All right, let's move on to our next case. We're scaling up from a bacterium to a huge puzzle from the front lines of HIV research. This one was a clinical observation that had a lot of people scratching their heads. So here's the paradox. You've got the standard treatment, antiretroviral therapy, or ART. It works great at suppressing the virus, but the moment patients stop taking the pills, the virus almost always comes roaring back. Then, a study comes out showing that a short 3-week course of these special antibodies, called bNAb, could lead to years of remission long after the treatment was over. I mean, how is that even possible? The mathematical model cracked the case by pointing out one absolutely crucial difference. Look at this. ART, for all its benefits, is kind of a one-trick pony. All it does is suppress the virus. That's it. But bNAbs, they have a 2-punch combo. Yes, they suppress the virus, but at the same time, they are actively stimulating and training your own immune system. And this second action has a name, the vaccinal effect. It's like a training program for your immune system. By coating the virus particles, the bNAbs basically put a giant kick me sign on them, making it way easier for your immune cells to spot them, grab them, and learn how to fight them off in the future. They're not just pausing the fight, they're teaching the body how to win the war on its own. And that's the core principle the model revealed. An HIV infection has 2 possible long-term outcomes. Either the disease progresses or your body gains control. All ART does is hold the system in a temporary artificial state. But the bNAbs, they fundamentally flip a switch. They push the body's entire dynamic into a new, stable state where it can control the virus by itself. It's the difference between hitting the pause button and actually changing the outcome of the game. Okay, for our final case file, we're going even deeper. We're tackling one of the most complex, most fundamental processes of life itself, figuring out the blueprint for how a cell divides. I mean, just think about this. The cell cycle is this incredibly intricate dance with literally thousands of different genes all playing a part. For so long, how all that was coordinated was just a black box. How does a cell possibly know which genes to turn on, in what order, at the perfect time, to pull off a flawless division every single time? The complexity is just mind-boggling. To crack a case this complex, you need a seriously sophisticated detective. And that tool is the Cybernetic Inspired Method, or CIM. Now, instead of trying to map every single one of those thousands of interactions, which would be a nightmare, this approach starts from a much smarter place. It assumes the cell has a specific goal for each stage of its cycle. Like its objective right now is grow bigger, or its objective is copy all DNA.
So the way CIM works is pretty slick. It starts by looking at all the data and inferring all the possible cause and effect links. But then, and this is the secret sauce, it filters everything through the lens of that stage-specific goal. It asks which of these links actually helps the cell achieve its mission right now. By doing that, it can throw out hundreds of irrelevant connections and distill everything down to the core network that's actually running the show. And the proof? You can then use that core network to predict what the cell will do next.
And the power of this is just wow. The model started with this tangled mess of over 700 potential interactions, but by the end, it had identified just 153 core connections that formed the absolute essential blueprint for the cell cycle. It just cut straight through the noise and found the real signal.
So, we've solved cases in bacteria, viruses, and our own cells. What's the unifying thread here? Well, it's about taking all this dizzying complexity and turning it into clear, actionable insights that can directly change the game for human health. To really see what I mean, I want you to look at this single number pulled out of the noise by one of these models, 2.65. It just looks random, right? But it's actually a critical switch for our health. What on earth could it be? Well, that is the precise tipping point for inflammation in our bodies. A model figured out that when the ratio of a key pro-inflammatory omega-6 fat to an anti-inflammatory omega-3 fat drops below 2.65, your entire metabolism literally switches into a less inflammatory state. It's just like that bacterial gatekeeper, a hard and fast threshold. This isn't some vague eat better advice. It's a quantitative, actionable target for your health. Now let's take that same thinking to a really tough clinical problem. Imagine you're a doctor with a sickle cell patient. They're on a critical medication, but they're not getting better. You're faced with a massive question. Is the drug simply not working for this person, or are they having trouble taking it every day? Getting that answer right changes everything. So researchers built what is basically an adherence detective. It's a model that looks at routine blood work, biomarkers the patient is giving anyway, and it works backward to figure out a likely dosing history. It can actually tell the difference between a patient who's taking the drug and not responding versus a patient who's struggling with adherence. It can even tell doctors how much forgiveness a drug has, how much a missed dose matters, giving them a powerful, personalized tool to help their patients succeed. And that's really the big story here. Whether it's finding a biological tipping point, flipping a switch in our immune system, or telling the difference between a patient's behavior and their biology, these models do one thing incredibly well. They turn overwhelming data into clear, actionable insights. They are paving the way for truly personalized medicine. Which leads us to one final, really mind-bending question. As these models get more and more sophisticated, as they start to integrate our personal genetics, our metabolism, our health data, could we one day have a digital twin of ourselves? A simulation so accurate that your doctor could test different treatments on it first to find the perfect one for you before you ever take a single pill? That's the future these detective models are building, one solved case at a time. Thanks for joining the investigation.